Hi, Dr. Anthony Revis here with Introductory Concepts in Polymer Chemistry by Dr. Anthony Revis, Chapter 6, Structure and Properties. When we take a look at the structure and property features of the polymer, thermodynamics has to be considered. And when we think of thermodynamics, one of the key factors is the activation energy. The activation energy, as you well know, is the energy required for the reaction to reach its transition state. So when we consider the activation energy for chain growth, that is making the polymer, is much lower than for initiation, that is starting the polymer. Okay, and that has to be considered, or that is one of the thermodynamic considerations. Another way of saying that is that the activation energy for depropagation, that is chain reversion to the monomer, is higher than initiation. In other words, once the initiation starts, the polymer wants to be formed. That's what it's saying. All the activation energies required to get to the polymer are favorable. Okay? Now, in growing the polymer, the growth velocity is less temperature dependent than initiation. In other words, you might need temperature or heat to get the reaction started, but once it's started, it really will be, for the most part, self-sustaining with, under reasonable conditions. So in other words, you might need temperature, but you won't need as much temperature to keep the reaction going as you do to get it started. All right? Now, when it comes to the way the monomers like to attack each other, the head to tail is more favorable. Therefore, substitution occurs in a fashion that favors the head to tail 1,3 position. Since the R group can stabilize the transient radical. In other words, the R is more electronegative than the hydrogen, and therefore, at that position, we can form a more stable radical. So again, the key concept with regards to substitution has to do with whether it polymerizes by a head-to-tail, a head-to-head, or a random attachment. The head-to-tail is by far favored because of the stability of the radical in the transition state. Okay, so these are some important thermodynamic considerations related to the activation energy required to form the polymer. Now, there's another way to visualize this or think about it thermodynamically is with regards to the Gibbs energy. Now, Gibbs energy with regard to polymers is a measure of the likelihood of reversibility. In other words, how likely is this to be a reversible process? All right. In other words, how likely will the polymer form? Okay, over remaining or going back to the monomer. So the Gibbs energy allows you to determine or measure or quantitate the probability that you will form polymer over staying as a monomer or reverting back to the monomer. And you know the equation for Gibbs free energy is delta G equals delta H minus T delta S. So now when we consider this equation, we can reach certain conclusions about what happens for polymers thermodynamically with regard to free energy, enthalpy, and entropy. Okay? Polymers then are typically chemically stable. In other words, they like to be formed. That's the bottom line. And because delta G is less than 0. So for polymers, if you do polymerization, delta G, it wants to go. It wants to form polymer. That monomer, which sits at a higher energy state, wants to be converted to the polymer, which sits at a lower energy state. Okay? That's what we see with regard to the entropy, delta S, being less than 0. Polymers are in a much ordered state, which means they're in a lower energy state. The more order, the lower the energy state. So your monomer is at a higher energy state, less ordered. Okay? And the polymer is lower energy state because it has a higher order. What you also find is that sigma bonds are stronger than pi bonds. There's no surprise there. Delta H, delta H is less than 0. Okay, so sigma bonds are stronger than pi bonds when we make these polymers. They're relatively stable because for the most part, they'll have sigma bonds. There are examples of unsaturated polymers as well, but many of the ones we see have most of the bonding that leads to the strength have to do with sigma bonds. All right. So now, here's what we also know. Thermodynamically, polymerization is favored when temperature of operation is greater than the sealing temperature. So that's basically saying that the polymerization is favored. Okay? All right, at equilibrium, which is really what we're talking about when we talk about our sealing temperature, we find that delta G equals 0, T will then be equal to TC, and we're making certain assumptions here that delta H of the polymer and delta H0 of the delta S0 of the polymer are independent of temperature. So those are the assumptions you're making. But essentially what this is saying is that at equilibrium, delta G equals 0. Therefore, again, we find that all the thermodynamic parameters favor polymer formation over monomer. That is the real bottom line of this. And that is the extent of the detail of which we will go into this. Actually, we could do an independent lecture on this as well. Okay? And we'll talk more about the sealing temperature in a minute. All right, the thermal instability of the polymer results when T delta S of the polymer overrides the delta H polymer, and thus that forces delta G to be greater than 0. So this is just the math here that we look at. So if you look at the equation, you plug these in when delta S overrides the delta HP. Therefore, we're going to get delta G, right, being greater than 0. And when that's the case, this results in depolymerization. Sealing temperature is another thermodynamic property or thermodynamic consideration that must be made. So the sealing temperature of the polymer is something that polymer chemists think about and examine. So what's sealing temperature? Sealing temperature is a measure of the potential for the polymer to depolymerize to the monomer. Keep in mind the definition that we use in this course have to do with those that are more practical to help you grasp the application of the concept. So when we think of sealing temperature, we think about, will it polymerize back to monomer? In other words, the rate of polymerization and depolymerization are equal at that point. And now the question is it going to move forward to more polymer or stay stable? The polymers are going to fall apart. And so that's when we examine the sealing temperature. So clearly the higher sealing temperatures are more favorable when it comes to the polymer. This means that the propagation and depropagation rate of reaction are exactly equal for a particular monomer concentration. So you look at the monomer concentration, you say at that point you have the propagation that is going forward to polymer versus depropagation going backward are equal. As it turns out, most polymers, you've already looked at the delta G considerations, polymer formation is by far favored over depolymerization to monomers. Now, there are two other things that we think about then that falls out of this argument or discussion about sealing temperature. One of the things we note is that sealing temperature is correlated to steric hindrance in the monomer. So we can look at the monomer and we look at it and we can correlate its steric features based on the R groups to its sealing temperature. Higher sealing temperature polymers tend to be commercially useful. That is the bottom line, and that's one key point they want to make sure you remember when, above all else, when it comes to polymers. Higher sealing temperature polymers, tend to be more commercially useful or find more applications commercially, and that's the purpose of polymers for polymer chemistry. That's one of the purposes, at least, for polymer chemistry. We show you this graphically where we have K versus temperature, a rate factor versus the temperature, and the temperatures in degrees K. And in this case, we find that T, for this particular polymer illustrated here, the temperature of sealing is above 550 degrees, and you note the crossing of the curves between the rate with regard to depolymerization, which has a steeper curve, and the rate and the concentration of monomer the rate of polymer times monomer shown with not quite as steep a curve. Then there's also the rate of polymer times monomer minus the depolymerization, which is shown in the dotted line. So the bottom line, if you examine this curve and you play with it, you'll be able to see the key principle here is that you're at equilibrium at the sealing temperature, and that's where the polymer makes the decision actually to go forward more times than not. But that's where the equilibrium occurs, where you have this this tug of war between polymerization, depolymerization, and polymerization wins more times than not. Okay, and again, it's proportional to the monomer steric properties of the monomer, and higher temperature tends to give you polymers that are more commercially useful, or at least industry is more interested in polymers with high TC for many of the applications. So, when we think about the thermodynamics, what are some basic conclusions we can reach, and what can we basically say about the thermodynamic considerations? One of the things we can say is that thermodynamics for polymerization addresses the position of the equilibrium between polymer and monomer. And we see this when we think about the sealing temperature. The other thing we can say is that for polymerization to occur, the Gibbs free energy for the polymerization is going to be less than zero. And that is the Gibbs free energy is less than zero. That means it's going to go spontaneously. It wants to go polymer's favorite. Also, the entropy is less than zero. Is typically for nearly all the polymerization processes, this will be the case. And so that's one of the factors you want to know. In other words, those when you consider the reaction for the monomer, it really wants to happen. Okay. The other thing that we can summarize is that polymerization is favored at low temperature, where T delta S is small. Depolymerization is favored at high temperature, where T delta S is large. So these are the other factors that we can consider, and we can summarize about the thermodynamics of polymerization. So let's just take a look at the impact of this thermodynamics when we look at in a table of some monomers that polymerize. We show you here 6 examples in this table. It's not a table you want to memorize. It just really wants to drive home the point about the impact of thermodynamics here. And when we talk about delta H, it means reaction or the process is exothermic when it's a negative value, and negative delta S means the reaction or the process is spontaneous. And you can see that the delta H and delta S for these processes are all negative, and that's what you want to be able to see. It's interesting to note that the ethylene here versus styrene in terms of its TG, ethylene does not have any steric hindrance in its monomer, but styrene does. And you note that the TG is lower for styrene than it is for ethylenes. And those are easy examples to look at. And then we have the alpha methylstyrene, which is more hindered, and therefore again you note here that it correlates again. There's a correlation between steric and the TG here as well. And then we go down to TFE, which has a pretty high TG, which makes it extremely valuable. TFE, Teflon, is well known for its high temperature properties. And now when we talk about correlation to steric, it's not just steric, but there are some electronic effects that have to be taken into consideration. So in other words, you have to compare apples to apples here. So when we compare the steric with regard to just the carbon-based groups, we can see that in the first four examples there. And then Teflon is basically an olefin to itself in terms of there are other considerations to take more than just steric when it comes to Teflon, and we're not going to go into any more detail on those. But suffice it to say that there's a correlation between the features on the double bond and the T sealing, and that is critical. In the earlier slide, we said there's a correlation between steric, but there's also just overall, perhaps a better statement would be that there is a correlation between the functionality on the olefin and the TG. And one of the factors in that regard is steric. And there are others that we have to consider as well. Okay? So, let's just talk a little bit further about some other outputs from understanding the thermodynamics. Examples of the monomer-polymer equilibrium. Let's just take a look at a few that are worth just discussing to help perhaps clarify what we mean when we talk about these thermodynamic factors with regard to the monomer going to polymer. We have ethylene is greater than isobutylene, okay? And so again, we just basically summarize these on this slide. So again, ethylene greater than butylene, attributed to steric hindrance along the polymer chain, which decreases the exothermicity of the polymerization. So in other words, you have to consider the steric factors when it comes to ethylene and isobutylene. In a similar way, as we've already pointed out, ethylene, styrene, alpha methylstyrene, steric factors along the polymer chain. So we're just basically reiterating these and summarizing them again. And then in 2,4,6 trimethylstyrene has the same delta H value as styrene. And it's interesting that this suggests that the major effect occurs from substitution directly attached to the polymer backbone. So slightly some other factors that we have to consider there. Okay. Again, it suggests that the major effect occurs, that there's a major effect that occurs for the substitution directly attached to the polymer backbone. So we have to take a look at the polymer backbones to really further understand these particular factors, and we show you those backbones here for you to take a look at, and gives you an idea of what these polymers really look like. Okay, and so we take a look at the polymer and take a look at these considerations, as we pointed out. It kind of helps you understand what might be happening there with regard to the thermodynamics of it. Okay. Another factor that we consider when it comes to characterizing these polymers and looking at what their interactions are and their properties is the impact of intermolecular forces. Okay, when we look at these, and we look at the polymer thermodynamics, and we look at how they are characterized, we think about dispersion forces. And dispersion forces are intermolecular forces created by attraction between molecules in the polymer that hold the material together. Essentially, these dispersion forces are what we classically call London forces, or we call London forces, okay, or essentially hydrophobic forces. They're like marbles rolling through a pipe. They roll freely, but they do have some interaction, but it's not a strong stick. But those intermolecular dispersion forces have the attractions that have to be overcome in some cases to use the polymer. And that when we stretch these polymers, for example, that stretching is called necking. And that necking pulls and then all of a sudden overcomes the dispersion forces between the polymer chains. And when that happens, the polymer chains stretch out and release the energy there. So it's kind of free the polymers to stretch out, and they overcome the again the dispersion forces so that they can form a neck in the polymer chain. So the necking of plastic illustrates the stress required to overcome these intermolecular forces, these hydrophobic forces, or these van der Waals forces there in the polymer. Now there are other forces that may be present as well in the forces in the polymers as well. So again, right now we're biasing on terms of being hydrocarbon polymers, where we essentially just have van der Waals forces or dispersive forces there in the polymer that have to be overcome to stretch the polymer. And this illustrates the presence of those intermolecular forces. That's what happens when you pull on the plastic. Next time you get a chance to stretch the plastic, you'll feel it. All of a sudden it pulls, then all of a sudden it gives, and it pulls very freely. That's because you've overcome the polymer chains, the dispersion forces between the polymer chains. Okay. A way of characterizing these polymers is by molecular weight. So we can characterize by molecular weight. Again, characterizing these polymers that have these intermolecular forces between these chains that are interacting. So you have this polymer, but those interacting chains form this polymer that we can characterize by molecular weight or molar mass, but more times than not, in polymer chemistry, you will hear me use the term molecular weight more than molar mass, because it's not, in polymers don't have really a pure molar mass. They really have a distribution of polymers that define its overall molecular weight. So one of the ways of characterizing these is by gel permeation chromatography, GPC. It is size exclusion chromatography, SEC, that separates polymers based on size. So you have this pail of polymers, different size marbles, different size balls in there, and they're all characterized based upon their size through size exclusion, meaning that you have this gel that has a surface, but there's more internal pore region in there. Inside the gel is a porous gel. Excuse me, I should point that out. It is a porous gel, and that porous gel has a pore diameter mouth opening, a cave. But inside that cave, inside that pore, inside that cavity, there's a lot of space there. So the smaller molecules will go into the cave, go into the pore, into the internal region of the gel, and will leave. And that takes time to do that. Whereby the larger molecules will see the pore, it won't fit, so it'll bounce against it and it'll bounce off and go on through the GPC. And what happens then is that the larger particles come out first. The large particle comes out first, followed by the smaller particles. Then the very smallest particles will come out. All right. Now, so this technique is used to determine the molecular weight of the polymer. Higher molecular weight fractions elude earlier in the chromatogram. And then you have to detect it. And there are various ways to detect it. We'll talk about some here. But here we have a detector. And basically there's 3 different detectors here. And they all give you the same message, really. It's what happens. This is not 3 polymers. This is 1 polymer. It's just showing an example of, depending on the detector you get a different shape curve, or you get a different value. Therefore, when you report molecular weight of a polymer, you have to tell how you measured it, which detectors were used, and there are factors and correlations and apps that will allow you to say whether or not that's the same as this one or the other. Okay, so here you have a LAS signal here for the first one shown in black. That gives you 1 reading. If you use a viscometer signal, you would get another. If you use an IR signal, you get another. And all the time, the chemists will take this, and they will do all three. And from there, the computer will run some algorithms, will run some math, and give you what a reportable molecular weight would be for this polymer using this technique with these detectors. Okay? And so the bottom line here is that gel permeation chromatography, that is the tool, that is the chromatographic tool used to separate the polymers based upon molecular weight, with the larger ones coming out first and the smaller ones coming out second. But the way we view it, the way we are able to see it, is by detection with LAS signal, some type of refractive index, viscometer type signals. And those, each one has a slightly different response in how it meters or reports that curve. And then the algorithms on the computer software will do its work and report a value back to you. Okay? So, as we point out and start to point out to you, molecular weight for a polymer is a mixture of different size molecules, and that's important to know. And therefore, you get a distribution of polymers when you analyze it, when you run the curve. They do not have a single molar mass value, which is why I don't talk about it as molar mass, and that's sometimes confusing to students when we talk about it. An average molecular weight is determined, okay, and so it's an average that we get. And again, it's done using size exclusion chromatography, GPC chromatography, where you get these three measures are made. Okay, and here are those three measures, and let's talk about them. Size exclusion chromatography reports or elutes the polymers based on molecular size, with the highest molecular weight coming out first. So the charts we show you here are in terms of decreasing molecular weight. I want to be sure that I said that clear enough. So we have what we call the number of molecules here. That is basically a count. It's like counting marbles in a pail, versus the molar mass. And so when we think of it, we have three different ways to look at this. We have what's called the MW, the MV, and the MN. So each of these has a slightly different way the values are reported and where in the elution the data is collected. So let's look at all three of these. The number average molecular weight is the total weight of all the chains divided by the number of chains. And we'll show you how these calculations are done in some slides a bit later. The weight average molecular weight, the average of the weights is basically the average of the weights. Okay, and that's what your MW is. It comes out the average of the weights, and it's obviously skewed toward the front end of the exclusion, because that's where the higher molecular weight ones come out. And it's higher than the MN. The viscosity average is by viscosity measurement. It's closer to MW than it is to MN, and that's just how the methods work themselves out. Where you have basically your MW comes out first, then your MV, then your MN, and it's all based upon size exclusion of the polymers. The two that use the most, frankly, are the MW and MN. Okay? Now, we point out to you that when we consider these, MW is used most often than the other two, the MV and MN, because MW is the bulk polymer value. So it considers the bulk polymer. It's more of what's reported as a bulk polymer value, and it's most useful towards its influencing, okay, the overall behavior of the polymer, and also what influences its physical properties. In other words, when we carry out a polymerization and you calculate or obtain the MW, which for the most part is done by apps and computer software, when you calculate the MW, you're getting a truer value or a better value of what the true molecular weight of the overall polymer is for that particular polymerization process. Okay, and so you have to keep that in mind when you do this. However, there are those who will use MV and MN for other types of purposes as well. All right. So how do we do these calculations? We're just going to go through here only to show you the difference in how it is, so you give an appreciation for it. Okay, so the number average is the total weight of all the chains divided by the number of chains. So this gives a true average weight. So we get an average weight when we get there. I want to know if you count up all the chains in the polymer, this would give you the average. And so this is going to be at the top of the peak. This is going to be the center of the curve, and so that gives you the average peak. But that average is skewed to the lower end of the polymerization of the chromatogram, of course. And so here we show you an example. If you count up all the chains, and let's say you had 2 chains at a million, and then 700,000 5 chains, 400,000 10 chains, 4 chains at 100, 2 chains at 50. If you went through, you have these 23 chains, right? And so if you add up the values, you get 10,000 for each. So you go through for each of the chains you have there, and what you discover is that when it all comes out, it averages itself out to about 435. Again, this is an illustration to show you what it looks like. So you'd have about 10,000 units there per 23. I'm sorry, 10 million per 23. So you take that 10 million and divide it by 23, and that's the value you get. Okay, and so that would give you your number average of all the marbles in there. The marbles add out of every ball, that's in there, every ball of polymer in there comes out to that average. Now, if you look at that number is lower than with the MW. Most of the polymer mass is in a heavier fraction, and that's what you have to keep in mind. So given the average molecular weight of the greatest polymer fraction, so it gives the greatest molecular weight of the highest portion of the polymer fraction. You get it? So you want to know the highest portion, you look for the MN. And we show you how that calculation is done, and you can take time and go through this in detail yourself. But it's essentially, it takes those fractions divided by the total count, and that total count times each of the fraction, run the numbers through, sum it, and you will get this value. So I encourage you to take time and go through this in detail. We won't bore you with that in this part of the formal lecture, but it is good to go through and learn how to do these calculations. Now, there's another important factor that is taken into account when it comes to molecular weight characterization. That is the molecular weight distribution, or the polydispersity, or the PDI. Okay, and that PDI, that polydispersity or dispersity index, is a measure of the distribution of the molecular weight as a ratio of the weighted average. Okay, and you now know what the weighted average is of that molar mass, and the number average, you now know what that is for calculating the molecular weight as well. It is an indicator of the chain's uniformity. How uniform is this? So what happens when this chromatogram is run, and when the software runs and gives you the values, what you discover is that you can take the cut of the MW, divide it by the MN, and you will get a dispersity, or a DPI value. And we show you that for an example of a curve done here. In this case, the way it works out, it's a frequency count, and the way the software works out, your molar mass is reported to the higher molar mass is reported to the right side in this case, because that's just how the software crunches the data and reports it. So you take that MW divided by the MN, and you get, in this particular polymer case, you get 1.8. That means that's not bad distribution for a polymer. Now, for some solids, for very high precision work, you want that polydispersion to be about 1.2. So when you get a polymer at about 1.8, less than 2, you kind of call it quits. You call it a day. You say that's not bad. So certainly, for some polymers, three's a good number. It depends on the application of the polymer. So when you get a polymer at about 2, you call it done. You say that's a good run for the day. So essentially, that means that when all is said and done, that distribution of polymers is pretty good for that particular polymerization. So let's talk about how you bring this molecular weight and degree of polymerization, or the DPI. And again, you'll see different terms for that. You'll see, PDI. You'll see PDI, and I don't know whether earlier I said DPI. You'll have PDI, and then you'll have DP. So it depends on how you like to talk about it, degree of polymerization, or you could talk about it as PDI, okay? Polydispersity index, okay? So we could take these and we can look at their ratios and look at their values to reach some conclusions about how we feel about the polymer. An example would be PVC. PVC produces a polymer of about 50,000 molecular weight. From a monomer, is about 63 grams per mole. That gives you a DP of 800. Sounds too large. No, their size is only relative and to the application. In other words, there's no magic number. But when you see a polymerization that runs at a very narrow one, that tells you how precise each of the steps are in that process toward the propagation steps are in that process, okay? And it tells you how consistent that process can attack those chains and create similarly distributed chains. Gives you a little bit of indication also of the rates that are going on there as well. There's a lot more you could talk about here. It's really be a fun discussion that you could have about this, just the simple DP or PDI, depending on how we talk about it. And there's, again, two terms that we use, and we show you both those terms in here so that you're aware of it. Okay? Now, but what you know is PVC works like it works, and it meets the in-use application. Therefore, this is exactly what it should look like. And now, once it's established at 800, you can't oversmart yourself by making one. Well, I think I want to make one with a lower polydispersed, with a lower DPI, or a little bit less of a PDI index, okay, or its polydispersity. Well, you don't want to do that because that changes the product, and that would change the performance expectation on how that product might be used. So there isn't a magic value for this. You basically make it according to what that manufacturing process needs to prove out its product. Okay? So, just some things to note here, and what happens when the increase molecular weight. Increased molecular weight, tensile impact strength increases. Resistance to cracking increases. Viscosity in the molten state increases. And resistance to being shaped increases. So these are important things to keep in mind when you increase the molecular weight of the polymer. And there may be others that you'll learn in the course, or you'll learn in some other areas. But these are some critical ones that we think about. Now, having said all that, what's important? The diagram on the right shows you what tends to be important when it comes to commercial polymers. You have the properties versus the molecular weight and the degree of polymerization. Okay, the DP or the PDI. polydispersity index. So basically what it amounts to, if you have viscosity, if you examine a viscosity curve, which is shown in green here, versus a tensile strength curve, you kind of have this sweet spot for these commercial polymers and where they like to be. It doesn't mean you can't have polymers above and below these, but this is a sweet spot. And in terms of molecular weight, that tends to be about 10 to the 4 or 10 to the 7 in terms of what you might see for a polymer. So basically, you got to get above 10,000. So we're somewhere between 10,000 and a million. You can get a pretty good. Polymer with some applications that commercial people would like and could turn into some useful product. So you outside that range, doesn't mean it won't work. Yes, there's some things that work, but typically this is kind of the sweet spot. And we show you that on here about where the viscosity and tensile strength, where it all kind of comes together and gives you a useful commercial product. So we mentioned the viscosity then, so let's tell you a little bit more about that, okay? And really it's an overview, which is the purpose of this course is to introduce you to concepts and tell you how these concepts are used and how industry gains value from these concepts and help you understand what plastics and what polymers are all about. Viscosity is an internal property of a fluid that offers resistance to flow. There's something internal about that polymer that resists flow. It is due to the internal friction of the molecules and mainly depends on the nature and temperature of the liquid. So basically, we mean the nature of the material of the polymer. What type of polymer is it? Is it highly what's the functionality? Is it hydrophobic? Is it hydrophilic? Is it branched? Is it non-branched? All these types of factors go into influencing the nature of it. Is there hydrogen bonding in it? And that really tends to influence it. Is it a polar polymer? Is it a non-polar? So you think of those factors. And temperature influences as well. So that's viscosity. It deals with that resistance to flow. Now, many methods are available for measuring viscosity of a polymer. The Oswald method is a simple method for the measure of viscosity, in which the viscosity of the liquid is measured by comparing the viscosity of an unknown liquid with that of a liquid with a known viscosity. So you're basically comparing yours against a standard. So there's some standards that have been established, and the viscosity of those standards are there, and really you're judging against that. Is it the same? Is it faster? Is it slower? That's a general way of thinking about it. Okay, relative to the standard is what happened. Okay. Now, in this particular method, the viscosity of the liquid is measured by comparing the flow times of the liquid, okay, with equal volume using the same viscometer. And it works out, you basically set up an equation here where you can calculate out the viscosity of the unknown based upon the equation. So when we just examine the equation here, and we show you the equation derived where it's N1, but actually perhaps we should have done it for you for N2, but it amounts to the same thing. Okay, so you can have the equation for N1, or you can have the equation for N2, and you can calculate it through basically your first factors are equal to your second, yourself a simple equality equation between the two. And so you have the times of the flows, you have the viscosities row, and you have the densities row of the polymers, the standard and the one that you're examining, and you have the basic viscosity set at water for the standard, and then you just calculate your second viscosity at the given temperature. So this is a straightforward set up the equation here, whether you set up for N1 would equal through, or you set up for N2, carry it through. Either equation that you use will give you the same answer, okay? But again, most of this is done now automatically, as you might guess. But this is just to help you understand what factors go into those automatic calculations. Now, when we consider the viscosity, we consider viscosity and the relationship between it and the average molecular weight. The molecular weight of the polymer is measured by use of viscometer, okay? And the molecular weight obtained by this technique is called viscosity average molecular weight. So this is where we get our viscosity average molecular weight. All right? And so this viscosity average molecular weight again is calculated based on this fact. It's calculated in this fashion. Excuse me. The molecular weight of the polymer solution is very high, so the viscosity of the polymer solution is very high compared to the pure solvent. So using these factors, and it's been well established, it is basically a straightforward technique for laboratory technicians who do this. There's an equation that comes out of this where we basically look at the intrinsic viscosity and its relationship to the molecular weight, and K and alpha are constants for a particular polymer solvent system. So you have to know the polymer solvent system, and you basically use the equation. But again, no one does this calculation by hand anymore. It's all in the app or in the software. But this is the exposure to the relationship between the intrinsic viscosity, the molecular weight, and there are some constants relative to the type of solvent you use. Now, with the known values of K and alpha for a given polymer solution, the intrinsic viscosity and therefore the molecular weight can be calculated using this equation, and that is the bottom line. That you can have the molecular weight, you can have the viscosity, and you can calculate. You can have the intrinsic viscosity, and you can have the constants for the polymer solvent system, and you can calculate the molecular weight. Okay? So you want to keep that in mind, that there is a way to do that, and that's where you get the viscosity molecular weight. All right? So here, this slide shows you some examples to give you an idea of what these viscosity look like, having talked about them. And they're measured in terms of centipoise. That is the most common way of measuring these. There are other ways. But they're reported here as centipoise, and it's all relative, and it gives you an idea. Water is 1. Okay? And so you kind of remember these large jumps in terms of it. And we have these different motor oils. So you see different motor oils. You can tell whether you have the SE10, 20, 30, or 40 based upon its viscosity. But you kind of think of water as 1, honey is 10,000, and peanut butter is 250,000. So it gives you an idea, or sour cream is at 100,000. So you have water, 1, honey, 10,000, sour cream, 100,000, just to give you an idea of what it's like. And castor oil is 1,000. And then you have everything in between. So oftentimes people, when they want to just ask you a quick question about the polymer, they'll ask you, was it like honey? And you'll say, no, it was thicker than honey, so you know it's above 10,000. They'll ask you, was it like sour cream or something? And say, yeah, but not quite as thick. You might say, okay, it's somewhere in the mustard kind of range. So people have these pictures and their ideas. They've heard these values so much, they'll ask you a question like, say, was it like milk? Yes. And okay, so it's really about 3 centipoise, so it's not really a polymer of any significance, or it could be a polymer that's been diluted in solvent or what have you. So, but these are things that they think about in terms of viscosities, and viscosity really rules when it comes to motor oils. Okay, well, a few more things rule, but viscosity is a critical one when it comes to that. When it comes to where you use oil in engines, viscosity is a critical consideration for them. Fiber thickness is another part that's thought about when it comes to polymer characterization and how these polymers might be characterized. What's the fiber thickness? Okay, so we have an example. You have examples here to give you an idea. Human hair is all over the map, anywhere from 17 to 181 microns. You basically have PTFE at 312 all the way down to the methacrylate, the butyl methacrylate, at about 60 microns. So this is just give an idea of what it's like, and polypropylene is 150. So it kind of gives you an idea if you looked at these in terms of fibers and thought about them as fibers, then these are the values that you would discover for them. There's a well-established thermal method of characterizing polymers as well, called TGA, Thermogravimetric Analysis. It measures the amount and rate, the velocity, of change in the mass of a sample as a function of the temperature or time in a controlled atmosphere. In other words, you basically burn the polymer and you take a look at how it falls apart over time. And each major degradation part from it, okay, gives an indication of what the polymer might look like. So basically, you're taking a polymer, this lump of polymer, you put it in an instrument, and it basically burns it, and you read the gases over time, or the materials the fragments from the material over time. So you're not actually reading the fragments exactly; you just read it mass loss. Okay, so you burn it, mass loss, burn it again, mass loss, burn it again, mass loss. So there's no mass loss. Okay. The measurements are used primarily to determine the thermal and oxidative stability of materials as well as the compositional properties. And compositional properties are pretty important. And people who get very good at this have gotten really good in their industry of predicting what is most likely lost from that as it goes. And if you do this enough, you get pretty good at it. You know, if you say, well, someone tells you, I have this polymer, and they tell you an idea what they did. These guys who've done this a lot can almost predict what the curves are going to look like in many instances, and they get very few surprises, and when they do, that's when the invention comes into play. Okay, the technique can analyze materials that exhibit either mass loss or gain due to decomposition, oxidation, or loss of volatile such as moisture. So oftentimes we'll have a material, and the first curve that comes out of the first degradated product comes out is simply absorb moisture. Okay. When these samples are handled, you have to be aware also that you can get another degradation due to handling it with your hand, oils and things of that nature, creams on your hands. So the samples are basically clean or not handled, or are properly handled when introduced into the instrument. So it basically burns them, and it burns off anything in it, including decompose the material itself. It is especially useful for the study of polymeric materials, including thermoplastics, thermosets, elastomers, composites, films, fibers, coatings, and paints. You name it, they get analyzed by TGA. Okay, this gives an idea of what types of volatiles also may come off, as in most coatings, volatile organic content is very important, and in coatings, outgassing of certain sealants and things of that nature is very important. So this gives you an idea of what might happen prior to putting it into the marketplace. So here's an example. Let's take an example. We're going to take a couple of examples here to show you what this looks like. Let's take the TGA of this particular homopolymer. Each change in the curve represents a weight loss event. Some events may be due to loss of just physically absorbed material on the polymer, like water or oils from your hand. In this case, we have one drop at 500 degrees C, which means that this is polymer is blown apart as one basically one piece fell off. Okay, so every time the curve drops, something fell off the polymer. And so you would take it and you would analyze it. If it's a gas, you analyze the gas. If it's a material that you can recollect and reconstitute in some fashion, you might do that. The other thing is you would take now the leftover polymer, if it indeed is leftover polymer in there or leftover material, you take whatever's left over in the port, you might analyze it further by some other analytical method to determine what was left there. So basically this curve shows is nylon 6 basically shows one drop. That's how you know you got nylon 6,6. That's its TGA. If it shows anything different, you got a problem. Okay, so there's a degradation, and basically essentially this tells you that this polymer falls apart at 500 degrees C. That's what this tells you. This polymer fell apart, fell apart at 600. So this could be a complete catastrophic loss of all the major linkages or some other segments in the nylon 6,6 polymer. But essentially, TGA tells it at 500 degrees, it falls apart as one piece, as one volatile piece or one broken off piece. Let's take something then a little bit more complicated. And that's what the take-home message is. Each drop in the curve is loss of a material. And the final one is what's left over from that. Okay? If anything. So you have TGA of this material. Okay? We have a tire elastomer. And this is a typical tire elastomer. It's blended polymer when you make tire elastomers. So you take it and you put it in, and we've already given you the answer by telling you what came off. But you notice there's the number of drops. You have 1, 2, 3 major drops in this material. And you have 1, 2, 3, 4 total plateaus where it rests. So the star material is 1, then it drops off. The first drop off was analyzed and found to be an oil in this particular blend. The next drop off was found to be degradation of the polymer from this particular blend. And then the third drop was found to be the carbon black fell apart from the network there. And then at the end at 800 degrees, you were simply left with the filler. So this tells you something else, that a tire elastomer is composed of at least 4 different types of materials: a filler, carbon black, polymer, and oil. So that is one of the things that you can answer. That could be a test type question someone might ask. They show you the TGA curve and say, well, how many materials were degraded? And you answer it. And then you use some judgment as to what you think those materials were. Typically, the lower molecular weight ones will degrade first, will fall. Then the next molecular weight, or the next one that's more susceptible to bond breakage, will break next. And then the third will be the one that's harder to break. And then the fourth sometimes never breaks. For example, silica never falls. It's just left there as silica. So we have a break then at about 350 degrees, which means this tire will start to fall apart at 350 degrees. Then it will continue to fall apart. It will hit again a little above 400 degrees, about 410 or so. Okay, then the next thing that falls apart is about 750. But by then you lost your tire. Okay, all right. So above 350 degrees, it falls apart. The oil's gone out of it. That means if the oil is gone, it's going to be less rubber. It's going to be that means it's going to be more brittle, which means it really wants to try to fall apart now as it goes along. And then once the polymer is left, you don't have a network. All you have is basic carbon black, and then that essentially just continues to just hold its temperature until it reaches its maximum for its next degradation. So that's what TGA will give you. Now, when we talk about polymer characterization, there's one other area that we want to introduce in this chapter that will be talked about in detail in the next chapter, which is chapter 7 for this particular class. But I'd like to introduce the concept now to expose you to it because it's an important part of polymer characterization, and it's called radiology. And we'll just share this slide and we'll talk about it in more detail in the next chapter. Radiology deals with the deformation and flow of both solid and liquid materials. And you want to be aware of that. It studies the flow of the liquid, soft liquids, and solids with plastic flow rather than deforming under the applied force. In other words, radiology kind of deals with how you take a polymer and basically beat it up, twist it around, pull it, press on it, and try to make it basically fall apart, or see how tough it is. How elastic is it? How tough is it? That's what radiology helps you do. So you bend it and you put it through basically some grueling tests to see just how tough the polymer is. That is a subject that we'll talk about in the mechanical behavior in the next chapter. The mechanical behavior is an expression of that radiology. And what do we talk about here in this chapter? We've talked about in this particular chapter how we characterize these polymers, about their molecular weight. The radiology is a part of that consideration. And in other words, its radiology will tell you something about those properties that we've already talked about. Okay? And this allows you to tie that the thermodynamic considerations to the practicality of how the polymer works. So the bottom line of radiology is that it allows you to tie the theoretical to practical. So you have the theoretical, you have these values, you have these numbers, so what? Radiology will examine it in a very practical mechanical fashion to see how it functions. And one of the ways it looks at that is the stress. Okay? How's the stress? Okay? Which is the force per area. And how does the material flow? Okay? So radiology associates the applied external forces and torque twisting around to the internal stress and strain. So you stress it, you strain it, and over some time, over a gradient, and the flow of viscosity. Shear is another form of stress. So these polymers are put under stress to see how they perform. Rubbers, plastic, and fibers, and other such polymers are characterized using radiological techniques that allow you to practically examine these polymers, having given consideration to the thermodynamics and to other physical property factors. Well, that ends Chapter 6, Introductory Concepts in Polymer Chemistry by Dr. Anthony Revis.